All right. Hello, everyone. Thanks for tuning in. Hope you're all staying safe and healthy right now. I'm going to be presenting a topic from my PhD work that we recently submitted to NWR. That topic is on the systematic evaluation of the impact of assimilating remote sensing profilers for forecasts of nocturnal convection initiation. I want to first thank my advisors, Dr. Shuguang Wang and David Stensrud, as well as our co-author, Dave Turner. And I also want to acknowledge the members of our OU math group, as well as the multitude of people involved with PECAN who helped collect and process the data used in this study. So, starting with some background information, nocturnal CI tends to be difficult to forecast both operationally and in numerical weather models, likely due to issues with a few problematic mechanisms, including nocturnal low-level jets, elevated moist layers, or the large spectrum of forcing mechanisms that can generate convection at night. Most nocturnal CI tends to occur between 4 and 8Z, while conventional profiling observations are only launched twice a day, aka radiosondes, and outside that window. Such mechanisms are also typically located above the ground, such that the data we do have during this period cannot easily observe these nocturnal CI mechanisms. Luckily, there was a great data set collected during PECAN that specifically sampled nocturnal CI events. These data include high-frequency thermodynamic and kinematic profilers, and assimilating such a data set could alleviate a large observational gap and improve forecasts of nocturnal convection specifically. Our recent paper demonstrated large positive benefits from assimilating this data set for a single case. However, nocturnal CI can be generated by a variety of mechanisms that occur at many different scales. Just to show a few of those types of cases that were observed during PECAN, we had large-scale frontal overrunning events, which most commonly occurred when the low-level jet interacted with a surface boundary. There were also events associated with apparent MCS forming either out in front or behind the larger system, as well as smaller-scale CI events, such as those generated along a bore or outflow boundary, or even pristine CI events with no clear forcing mechanism. So apart from the outflow boundary category, most of these types of nocturnal CI events are driven by elevated mechanisms, meaning without frequent profiling observations, we cannot easily see such events. Additionally, these types of events are so dynamically different that evaluating the assimilation impacts for a single case is likely insufficient. Luckily, we had this very nice data set from PECAN that I mentioned earlier. The data collected include ARIES, which are thermodynamic profilers, as well as Doppler lidars and radar wind profilers, which measure wind speed and direction. And all three of these remote sensing profilers feature much higher temporal frequency compared to conventional data sets like the radiosondes. However, they typically only record data up to about 3 kilometers above ground level, and are also less accurate overall than radiosondes, so they typically feature much larger instrument errors. And that gets us into our main scientific question, which is, can assimilating a high-frequency but less accurate network of ground-based remote sensing profilers alleviate the data gap between radiosondes and provide a systematic advantage for forecasting nocturnal CI? Okay, so for the experiments we're running, we'll be applying a GSI-based ensemble Kalman filter assimilation system. We initialize our 40 ensemble members from the operational GEFS and SREF ensembles. First, we perform assimilation on the outer domain, the outer 12-kilometer CONUS grid. It consists of conventional PECAN data assimilated for 3-hour cycles for 12 total hours. After that, we downscaled to an inner convection allowing domain at 4 kilometers, where we also assimilate radar data in addition to the conventional PECAN data. After an hour and a half of assimilation on that inner domain, we initialize our forecast on a 1-kilometer grid. The exact location of that grid changes for each case, but the size is consistent. And each of the simulations are initialized relative to the observed CI event, meaning the DA period always ends 3 hours prior to the CI event that we're trying to capture for each of these cases. Speaking of the cases, we've selected 13 nocturnal CI events from PECAN. This allows us to evaluate the observation impacts for a variety of different CI mechanisms. We'll be evaluating these impacts using 4 different experiments. First is SON, where only the conventional data set and PECAN profilers are assimilated. Then there's SON TQ-Prof and SON UV-Prof, where we add in the thermodynamic and kinematic profilers respectively. And finally, SON All-Prof, which assimilates all data together. So for each experiment where we assimilate radiosondes, which is all of them, we only assimilate the radiosonde closest to 0 UTC, as long as a radiosonde was launched within an hour of that. That allows us to treat the PECAN radiosondes as sort of a quasi-operational data set. That way we can evaluate the impact of adding on the available thermodynamic and kinematic profilers. And another thing that I haven't mentioned yet is that we only want to evaluate the impact of assimilating co-located data. So it's been suggested in the past that if we were to introduce a new observation network, that we add it to a pre-existing network, such as the radiosondes. That way we can take advantage of that existing infrastructure. Thus, we only assimilate PECAN sites if they feature a radiosonde within an hour of 0 UTC and both a co-located area and kinematic profiler. And this ends up having between 2 to 7 sites assimilated per case. Now, I showed this slide earlier to introduce the PECAN dataset, but I also want to highlight the numerous pre-processing and quality control checks that we apply to these data in order to clean them up. But most importantly, we merge the radar wind profilers and Doppler lidars into a single composite dataset that we call composite kinematic profilers. Since one of the goals of this project is to focus on assimilating co-located datasets, if we treat the Doppler lidars and radar wind profilers as part of the same dataset, that increases our number of potential observing sites assimilated for each case. And the way we do this composite is discussed a little more in the paper, and we'll go through it here. Now, getting into verification techniques, because CI is locally rare and instantaneous, applying normal grid-based verification metrics can be very difficult. Typically, neighborhood probabilities tend to be very low, given how CI might only occur at a single grid point. So we're applying a new object-based detection algorithm that's adapted from Burkhardt et al. 2014. And it's a pretty simple technique. Basically, we start with identifying convectively active objects based on regions of composite reflectivity greater than 35 dBz. And we look for this threshold at the -10 Celsius level. And that allows us to remove any potential bright banding effects that could lead to spuriously large reflectivity and spurious CI objects to be detected. Then we track these objects backwards in time to find their starting time and location, and those two properties make up the CI object. And we apply the same method to both the forecast data and MRMS observations. That way we can verify the forecast quality using both deterministic and probabilistic methods. So here's an example of the output from the object-based detection for observations on top and forecast data on the bottom. Each dot overlaid on this slide represents a CI object. So we can see that for the observations and the forecasts, we're doing a pretty good job at detecting the new cells developing along this CI event that forms along an outflow boundary. For the deterministic verification, we would match between these specific observed and forecast objects based on spatial temporal thresholds. So if the potential object pairs are less than 150 kilometers apart and their initiation time is less than 2 hours apart, then we consider them a match. We picked these thresholds to represent sort of the subjective limits of a successful forecast. If there are multiple potential matches, we calculate this composite error, which basically combines distance error and timing error into a single metric, and then we would match the pair that has the lowest composite error. Once we've matched between the pairs, then we can calculate standard contingency metrics such as probability of detection, false alarm ratio, etc. So for the probabilistic verification, we accumulate all objects over a 1 hour window and then calculate neighborhood maximum ensemble probabilities. And MEP basically measures the probability of an event occurring within X kilometers of a region. There's an example for the same case shown here. We can see that the forecast is indicating a few different hotspots of CI, first along that outflow boundary, and then a couple spots behind the MCS, and then the model is also indicating the northern extent of the MCS as being a location for favored development. The observations show most of those same areas except that northern MCS point. We're not really seeing much observed CI there. Once we have both of these probabilities calculated, then we can verify them using fraction skill score. So that wraps up our methods, and now I'll move into the results. I want to start by showing the probabilistic verification of precipitation instead of just CI, and this gives us a good baseline of understanding the impacts of assimilating these data for nocturnal convection in general. This is fraction skill score, so a higher value would be a more skillful forecast. And we can see from this time series that in general, the SON-TQ-PROF experiment is more skillful, especially during later lead times, than the baseline SON experiment in black. This means that we're seeing positive impacts from assimilating the co-located thermodynamic profilers. Conversely, SON-UV-PROF in purple is at all lead times producing lower skill compared to the baseline. Looking at the distribution of the impacts, we can see that assimilating these wind data lead to a skill decrease for nearly all the cases. Now looking at the same verification but for the CI objects, first we can note that the CI is showing much lower skill compared to precipitation. This might not be surprising, but it suggests that our model can predict general regions where nocturnal precipitation occurs, but it struggles to predict the precise timing and location of initiation within those regions. But back to the impacts. The time series here is a bit noisier due to many fewer CI objects compared to precipitation regions. But if we focus on the box and whisker plots, we find similar findings that the thermodynamic profilers are generally improving the skill of the CI forecast, while the kinematic profilers are decreasing the skill. I'll note that these impacts are small, on the order of about 0.01 fraction skill score, but we'll see through later slides that these results are consistent. So moving on to the deterministic results, this slide shows the contingency metrics for the matched object pairs. I'll note that the first 4 rows here verify over all CI events within the domain, whereas POD specific is only calculating the probability of detection for the specific CI events that are linked to the main ascent mechanism for each case. And again, we see small but systematic and consistent benefits from assimilating the thermodynamic profilers. So we see in green our best values for all these different metrics are produced in SON-TQ-PROF. So we're getting a higher ratio of hits, fewer misses, and an overall more skillful forecast when we assimilate the co-located thermodynamic profilers. And again, conversely, we're seeing some of the lowest values produced in SON-UV-PROF, meaning that the kinematic profilers are by and large degrading our forecast for detecting nocturnal CI. When both sets of profilers are assimilated at the same time, the result ends up being somewhere fairly close to the baseline SON experiments. This suggests that the positive impacts from assimilating the thermodynamic profilers are being counteracted by the negative impacts of assimilating the kinematic profilers. Now, while we do see negative impacts for the detection of CI when assimilating both data sets, we do see some benefits in other areas. So this slide shows attribute errors of the matched object pairs. So for example, looking at the timing errors of all the hits. And we see here that the best forecasts for the objects that are matched are produced when assimilating both data sets together. So we see the lowest timing, distance, speed, direction, and orientation errors in SON-ALL-PROF. Now, those previous statistics were mean impacts, while here we present this performance diagram that shows the spread between cases. So for this plot, a better forecast would be closer to the top right corner. And we again see in terms of the mean, which are these larger dots in the middle, that SON-TQ-PROF is giving a slightly better forecast compared to the other experiments. However, there's a lot of case-to-case variability as indicated by the different symbols for the different cases. So we have some cases like June 6th, given by the squares, where assimilating both data sets in green gives us our worst overall forecast. We have other cases like June 24th, where we saw a large positive impact from assimilating both data sets. So overall, there's a lot of variability between the cases. And we've done a little bit of work to try and understand this, and we think the case-to-case variability comes down to 3 main things. First, the location and number of observing sites assimilated for each case. So we found slightly better impacts when more cases are assimilated, but the variability is also linked to the case mechanisms as well. So this shows an analysis where I categorized each case as either strongly or weakly forced based on the presence of an upstream trough. And we find that the weakly forced cases show very little impact, while most of the mean impacts are related to the strongly forced cases. So this suggests that much of the case-to-case variability could also be related to the synoptic regime or the dynamics of the convective system itself. Next, to try and understand why the thermodynamic profilers improved the forecast while kinematic profilers often degraded it, I'll be looking at composite time height cross sections plotted relative to the observed CI event, and we'll be looking at these for each of the convective ingredients. So first up, I've plotted differences on divergence for each of these experiments. So this plot basically shows the impacts to the divergence field when assimilating the thermodynamic profilers, kinematic profilers, and both profilers together. We see that in general, most of these plots look very similar. So both sets of profilers, assimilating them increases the low to mid-level convergence about an hour and a half to a half an hour prior to CI. However, if we look at the impacts to water vapor, which is shaded, and temperature, which is contoured, we now see opposite impacts resulting from assimilating the thermodynamic and kinematic profilers. So the thermodynamic profilers, which directly measure these variables, introduce moistening on the order of about half a gram per kilogram and slight cooling prior to CI, whereas the kinematic profilers introduce drier air and mostly warming, mid-level warming prior to the CI event. And when both sets of profilers are assimilated, it ends up being somewhere in the middle, so somewhat neutral impacts. And we can really put this into context by looking at the impacts to CAPE and SYN. So we're seeing cooling and moistening from thermodynamic profilers, which leads to an increase in CAPE and decrease in SYN at about 500 meters above ground level, leading into that CI event. This would make elevated parcels more likely to reach their LFC and produce convection. Meanwhile, assimilating the kinematic profilers does show a small increase in CAPE, but more so there's a stronger signal for a decrease in CAPE above the 500 meter level. So just to summarize, we find opposite impacts to the pre-convective thermodynamic variables when assimilating these two data sets, and we hypothesize that this is the main reason why assimilating thermodynamic profilers enhances our detection of CI, while assimilating the kinematic profilers degrades our detection. Now, in this final section of results, I'll go through a couple of example cases to better illustrate some of these impacts. The first of these cases is 24 June, which was a frontal overrunning event where we saw positive impacts from assimilating both data sets. These plots show neighborhood ensemble probabilities of reflectivity greater than 30 dBz, with the observed reflectivity contoured in black. So we can see here that compared to the SOND experiment, adding in those thermodynamic profilers greatly enhances the probabilities for this new convection, while assimilating the kinematic profilers removes some of that spurious convection in northeastern Nebraska and better constrains the location of the event. So when we assimilate these data together, we get our overall best forecast with high probabilities and a pretty good location that matches the observed convection. So to show why this is the case, first we can look at 700 hectopascal dew points. Assimilating the thermodynamic profilers in the top right enhances the mid-level moist layer by about 1 to 2 degrees Celsius near the region of CI. In this circled region, change does get represented in SOND-ALPROF by some slight increases in dew point temperature there as well. Whereas assimilating the kinematic profilers mainly improves the forecast through modifying the mid-level wind field. So this is looking at 800 hectopascal wind speeds and convergence. We can see that in SOND UV-PROF, the ambient wind speeds are increased throughout much of eastern Nebraska, and this has the impact of weakening the wind gradient and thus reducing the convergence in northeastern Nebraska, especially compared to SOND TQ-PROF. So while SOND TQ-PROF is adding that additional moisture, we're also seeing a lot more convergence when we assimilate that thermodynamic data, and thus when we assimilate the wind data as well in the SOND-ALPROF experiment, it brings some of that convergence back down to baseline level. So this means that basically when both profilers are assimilated, we're seeing reduced convergence in this region where there shouldn't be any convection, and that means the kinematic profilers can help clean up some of that spurious CI. And finally, I'll show a case where we saw negative impacts from assimilating the kinematic data, that being June 26th. Again, starting with the neighborhood ensemble probability plots, we see that compared to SOND, SOND UV-PROF has lower probabilities in two main regions where we observe CI. First is this primary kind of arcing band. You can see how SOND UV-Prof is missing some of those new cells that form in SOND. And second, this kind of second linear trailing CI event that forms behind the primary arcing event. And you can see in SOND UV-Prof that that event is almost entirely missed. Another thing to point out for this event is how much better SOND TQ-Prof is doing. So for this arcing shape, we're seeing a lot better match of those probabilities to the observed event. So again, for this case, very helpful forecast when assimilating those thermodynamic profilers, but forecast degradations from assimilating the kinematic data. Now, we mentioned earlier that on average, assimilating the kinematic profilers results in drying near the region of CI, and we can see that in this animation for the June 26 case. Each image is one of the DA cycles, and the cyan triangles indicate a kinematic profiler assimilated at that time. So we can see, let it loop back to the beginning there, that early on in the data assimilation cycles, we're seeing a lot of dry air introduced. And that dry air eventually gets advected further northeast into the region of CI. So primarily, a lot of that dry air is originating in central and northeastern Nebraska, but it later gets advected and impacts the CI location. So to examine that a little further, we can look at the kinematic profiler assimilated from this site, which was FP3. Here I'll point out that the solid black contours are ensemble mean water vapor mixing ratio, contoured every 2 grams per kilogram. And since I can't really go back in the slide recordings, I'll just mention that there is this positive north-south gradient in moisture here. So looking at the left plot, which is the example wind profile assimilated, just the V component, we can see that above 1.5 kilometers, our observation is indicating a much lower V wind compared to the background, and that ends up getting our analysis pulled to the left as well. So that assimilating this observation weakens our V wind component by about 2 to 3 meters per second. And if you compare that with the previous slide, you can deduce, given this positive north-south moisture gradient, that a slower V wind would reduce moisture advection to central Kansas and cause drying compared to the baseline experiment. So we hypothesized that the upper portion of this kinematic profiler is what's causing the drying. And we found this occurring on a few example cases. So when we look for the cases where the kinematic profilers are causing a forecast degradation, often it's linked to drying in the upper portion of some of these kinematic profilers. Now, assuming the observation error for these data are correctly diagnosed, then we should still get useful information from the profile, meaning that if the error variances are correct, it shouldn't technically degrade our forecast. However, the right plot here shows the observation error assigned for these data in black, along with the root mean square deviation between observations and co-located radiosondes assimilated at that same site. So that basically gives you kind of an estimate of the instrument error. And what we can see is that the assigned observation errors are often a lot lower than even just the instrument errors diagnosed in red and green, especially above 1.5 kilometers and especially for the V-wind component. That means that the observation error assigned, which should include both instrument error and representation error, which tends to be pretty large for remote sensing data, our observation error is likely very underestimated. And this could cause problematic observations near the top of these profiles to be weighted more than they should in the analysis update. So we suspect that one of the main reasons why these kinematic data are causing this negative impact is due to these underestimated observation errors. So in summary, we find that assimilating the thermodynamic profilers retrieved by ARES can provide a small but systematic improvement for the detection of CI. We hypothesize that this is due to mid-level cooling and moistening introduced by the thermodynamic dataset, which enhances the potential for elevated parcels to produce convection. And this result holds true for both deterministic and probabilistic verification metrics. So conversely, assimilating the kinematic dataset often degrades the detection of CI objects. However, I'll mention again that assimilating both datasets together did lead to improvements in CI timing, location, and orientation. So we suspect, again, that this degraded forecast quality in SON-UV prof is likely related to opposite impact to the convective thermodynamic fields, and we suspect that that in turn is linked to underestimated observation errors. So like I mentioned at the start, this project has recently been submitted to NWR, so hopefully you'll see it out there soon. We've also used these results to motivate our next project, which is looking at optimal methods for diagnosing observation errors for remote sensing data in convective scale TA systems. And for that, you can stay tuned. So thanks for watching, everyone, and stay safe.